Hello everyone, welcome to my YouTube channel MechE-FUNdaMENTALs. In this video, I will discuss about the domestic refrigerator, its working, and the different components of the refrigerator. In the series of Fundamental of Mechanical Engineering, the topic is the domestic refrigerator, in which I will discuss about the component of the refrigerator, the thermodynamic cycle of the domestic refrigerator, that is the vapor compression refrigeration cycle. As R134A is the commonly used refrigerant nowadays, so I will talk about its pressure enthalpy chart, which is generally used for the design and the analysis purpose, and at last about the performance index of the refrigerator. Now the first one, that is the main component of the refrigerator. If you see, you look the fridge like this. So these are the different components which is in the refrigerator. You see the first one, the first main component, that is the compressor. So that is just near the floor because that is a vibrating component, and definitely for the stability that is near to the floor on the back side. The next, that is the condenser. If you see the fridge, the back side, then you see these coils. And these coils are the condensers, and we have the fins are also attached to increase its heat transfer area, to increase the amount of the heat dissipated to the surrounding. The third component, that is the expansion valve, and generally in the refrigerator the capillary tube is used as the expansion valve. And the fourth main component, that is the evaporator, which is actually the cooling coil, which extract the heat of the inside cabin to get the cooling effect. So if I talk about the components or the main component of the refrigerator: compressor, condenser, expansion valve, and the evaporator. So these are the four main components of any refrigerator. The next is the vapor compression refrigeration cycle, which is actually the thermodynamic cycle of the domestic refrigerator. So here you see again the main component of this particular cycle. You see the compressor, condenser, expansion device, and the evaporator. So these are the four components in which that cycle operates. And you see the different states. That is the state 1, this is the state 2, this is the state 3, and this is the state 4. So these are the different states. States of what? That is the state of the refrigerant. And the commonly used refrigerant nowadays in the domestic refrigerator, that is R134A. Its chemical designation is 1112 tetrafluoroethane. So the refrigerant actually flow in that thermodynamic cycle, which is the vapor compression refrigeration cycle. So to explain the working, definitely we have to talk about the states of that refrigerant: 1, 2, 3, and 4. So the vapor compression cycle involves four main components of the domestic refrigerator: the compressor, the condenser, the expansion valve or the throttle valve, and the fourth one, that is the evaporator. Now, as in this slide, I am talking about the working of the vapor compression refrigeration cycle so that we can understand how the domestic refrigerator works. So you see here, this is the schematic diagram or the block diagram: compressor, condenser, expansion valve, and the evaporator. And to understand that thermodynamic cycle, we required some property diagrams. So this is the first property diagram, that is the pressure enthalpy diagram. So this is known as the pH diagram. And the second property diagram, which actually also we use for the analysis purpose, that is the temperature T and the entropy S, TS diagram. So this is the pH diagram of the vapor compression refrigeration cycle, and this is the temperature entropy property diagram of the vapor compression refrigeration cycle. So in these two diagrams, you see the different state of the refrigerant. So this is the state 1. So you see this is the state 1 in the pH diagram, and this is the state 1 that is in the TS diagram. So according to the processes, let us suppose 1 to 2 process, that is on the compressor. So you see that process 1 to 2 in the pH diagram as well as in TS diagram. So this 1 to 2, that is about the compression. So that compression, there is isentropic compression, and whatever the work you are doing in that system, as you know, to operate the domestic refrigerator, you give the electrical supply, and that electrical supply converts into the mechanical work by the compressor. So the compressor is doing the conversion of the electrical energy into the mechanical energy, and that mechanical energy actually used to compress that refrigerant, and definitely state will change from 1 to 2, like that, 2 to 3. So that process is in the condenser where the heat rejection takes place. So 2 to 3, this is the process in the pH diagram, and this is the 2 to 3 process, this is in the TS diagram, you see. Then 3 to 4, this is the process in the expansion valve, and you see here, so this 3 to 4 process, that is the expansion process in the PS diagram, and this is the 3 to 4 process in the TS diagram. And 4 to 1, that is the process in the evaporator where the heat extraction takes place, so that we get some cooling effect. So this 4 to 1 process, this is in the PS diagram, and this is 4 to 1 process, this is in the TS diagram. So definitely I will elaborate the use of the PS diagram and the TS diagram. So how we analyze that particular cycle, and in the next slide, definitely that you know. Now here, now one by one, I split the processes to better understand. So this is the slide where I talk about the different processes in the vapor compression refrigeration cycle. So the first process which I pick, that is the process 1 to 2. So already I talked about, so that is process 1 to 2. Now see, I am focusing here only in the compressor. So this one, that is the suction side of the compressor, and 2, that is the discharge side of the compressor. Okay. So you see in this PS diagram also, I will connect that particular block diagram with the PS diagram also. So this is the state 1. Okay. So this is actually the saturation curve for that particular refrigerant. So I am talking the PS diagram. So this PS diagram is for particular refrigerant. Okay. So here I'm talking about R134A refrigerant. So you can imagine this PS chart is actually of R134A. So you see, this is the critical point of the refrigerant, and this part of the curve, this is the saturated liquid curve, and this is the saturated vapor curve, and this topmost position, that is the critical point. So at the state 1, that is the suction side of the compressor, the refrigerant is the saturated vapor. So when the refrigerant is saturated vapor at that particular pressure, so this is the pressure of the evaporator pressure, or you can say that is the suction side of the pressure. So you can mark here, this is the pressure P1. So that is the P1, or you can say that is the evaporator pressure PE. Okay, and also you can say that is the suction pressure in the compressor. Okay, so that particular pressure, this is the saturated vapor. So in this pressure line where it will cut this saturation vapor curve, so that will give you the state 1. Okay, so this is the state 1 when at that particular low pressure or the evaporator pressure or the suction pressure, the saturated vapor condition is represented. So 1, that is the state of the suction side of the compressor of the refrigerant. Now see 1 to 2. Now you are doing some work on that compressor. It means, and that work to compress that refrigerant, and ideally we know that is actually the isentropic compression. Okay. If you are giving some work on that particular refrigerant, you see here. So in the x-axis there is the enthalpy. So what is the meaning of the enthalpy? Enthalpy means that is the stored form of the energy in that refrigerant. How much heat energy content in that refrigerant, that is given by the enthalpy. If there is a state 1, so corresponding we have some enthalpy. Let us suppose I mark that will be H1. So H1 is the enthalpy with respect to the state 1. So when we do some work on that compressor, it means we are giving some work during that process. So definitely that work will be absorbed by that, by using the conservation of energy. Whatever work we are doing here, if I am assuming there is no loss of energy, so whatever the energy or whatever the work we are giving to that refrigerant, that is it's stored in that refrigerant, so enthalpy will change definitely. So at 2, the enthalpy is H2. The enthalpy is H2. So you see the work input, that is the compressor work, and that is given by the change in the enthalpy, that is H2 minus H1, and that is the specific enthalpy. It means that is the heat energy content per kilogram of the refrigerant. Okay. So by this pH chart, in that particular process of the compression, we can find out how much work we are actually giving to that particular refrigerant by the difference of H2 and H1. Now the second process, again you see here, so that is 2 to 3. So now 2 is this position. This is the superheated vapor refrigerant actually, because this is the saturated vapor at 1. So when you give some work and its enthalpy increases, so definitely this is the superheated region. As I already told you, this is the critical point. This is the saturation vapor, and beyond the saturation vapor, we have the superheated vapor. And the left side of the saturated liquid, that is the subcooled region. So this is the subcooled region. So here inside, this is the wet condition of the refrigerant. So there is a wet plus vapor, and the right side that becomes superheated. So 2, that is a superheated condition of the refrigerant. So here, this is the discharge part or discharge side of the compressor. Now in the condenser, the heat rejection will take place. So here at 2, the enthalpy is H2, already I told you. Now the heat rejection means during that particular condensation, it means the refrigerant will convert from vapor to the liquid. So here it is superheated vapor. And at 3, this is the saturated liquid line. So at that particular pressure, you see with the help of the compressor, you increases the pressure from P1 to P2. So here the low pressure, this is the P1 or the evaporator pressure, and this high pressure, this is P2. And this P2 is actually the discharge pressure, you can say, or you can say that is the condenser pressure. And at that condenser pressure, this state 3 will give the state that is the saturated liquid. So 2 to 3, the heat rejection takes place. The refrigerant will convert from superheated vapor to the saturated liquid. Okay, so this is the process 2 to 3, and that is in the condenser. Okay, so now the next process, and you see here again the heat rejection, how much heat is rejected, because here the enthalpy is S2, and this is here the enthalpy is S3. And again you see you have a horizontal line because the pressure is constant. But as you lose the energy, then definitely the enthalpy will decrease. So how much heat is rejected in the condenser? That will be S2 minus S3. Again, that is kilojoule per kg, because that is the per kilogram of the content of the energy in the refrigerant. And here you see the high pressure superheated vapor. So that is the state 2, and that will convert into the high pressure saturated liquid. So in the condenser, superheated vapor converts into the saturated liquid, and definitely the pressure is high, because at the suction side we take actually 2 parts of this one. This is the suction part of the compressor where the pressure is low, and this is the discharge part or the condenser part, and here the pressure is high. So we can say that this vapor compression reference cycle works between the 2 pressure limits, that is the evaporator pressure and the condenser pressure, or the suction side of the pressure to the discharge side of the pressure. Now see the next process, process 3 to 4. So this is the process 3 to 4. Now here you see this is the 3 and this is the 4. So this is the expansion process, and this expansion, this is the isenthalpic expansion. Enthalpy is constant. It means there is no interaction of the heat and the work during that process. You see we have the vertical line downward. It means the pressure will reduce because expansion takes place, but the enthalpy is not changing. You see here the enthalpy is S3 at the state of 3, and here this is the 4. So S3, that is equal to H4. It means during expansion or during throttling process, the enthalpy is not changing. So that process is known as the isenthalpic expansion, but definitely the pressure will decrease. Okay, so here at 3, we have the saturated liquid, and when you see 4 point and that particular pressure, so that is in between the saturated liquid and the saturated vapor, somewhere here. So it is low pressure liquid plus vapor phase, and definitely you see the liquid part is more than the vapor part. Okay, so here the enthalpy at 3, that is the enthalpy at 4. And now the main process as far as the cooling effect is concerned, so that is the process 4 to 1. And during that 4 to 1, the heat extraction takes place. It means you have to give some cooling effect in some space. Let us suppose this is a space. You have to extract the heat of that. So you can imagine this is the inside of the domestic refrigerator. So that refrigerant will enter at the state 4. This is the 4. This is the 4, that is the entry to the evaporator, and 1, that is the exit to the evaporator, and or you can say that is entry to the compressor. And during that, in this evaporator, actually the evaporation takes place, because at 4 we have the liquid plus vapor refrigerant. Liquid is more, and then when that will take the heat, because the boiling point of the refrigerant, that is very low, and that depends, that is a selection criteria of refrigerant, what temperature actually you want to attain in that space. Accordingly we select the refrigerant. Okay, so the boiling point is very low. So as that refrigerant exposed to that particular space which you have to cool, so that will boil, or you can say the liquid will convert into the vapor. So at 1, that is totally vapor. It means that is a saturated vapor. So what amount of the heat is added in that particular process? That is H1 minus H4, because here the enthalpy is H1 and here the enthalpy is H4, and the heat which is extracted by that refrigerant, so that it will convert into the saturated vapor, that will be H1 minus H4. And this is the refrigeration effect. And this is the refrigeration effect by which you are maintaining some temperature below to the surrounding in that particular space. And now you see this is the pH chart. So here, which I already told you about the pH chart, the pressure enthalpy chart, and the enthalpy is the main thing which you have to observe in different state, and definitely that is with respect to the pressure. So this is the R134A pH chart. So with respect to the refrigerant, we have the different pH chart, and that will depend what type of the refrigerant you are using. So here you see this is the pressure, the unit is you see that different units of the pressure, and in the x-axis this is the enthalpy kilojoule per kg. Now you see this is the state 1, that is the entry to the compressor, this is the exit to the compressor, the discharge side, this is the exit to the condenser, and this is the after expansion valve. These are the different states. Okay, so in this we draw that pH chart or the pH diagram in the pH chart of R134A. How we draw that? You see these blue lines, these are the temperature lines. You see 20 degrees Celsius. So this is the 20 degrees Celsius constant temperature lines. You see these blue lines. Okay, so let us suppose at the suction to the compressor you measure some temperature. Definitely we have the thermocouples to measure the temperature. If you know the temperature, and definitely also you know the pressure at 1, the pressure that we can measure by some device, also we can measure the temperature. So in that particular temperature line, let us suppose you get some temperature, you have to follow that temperature line in the pH diagram like this. Let us suppose this is the temperature. So that temperature you have to mark, and this is the pressure. You see, this is the point. You see, you measure the pressure is somewhere here. So this is the pressure line, this is the temperature line. So where that will cut, that will give you the state 1. It may be sometimes superheated region also. That depends. What is the temperature and what is the pressure? So its intersection will give you the state 1. So from here you can find out what is the enthalpy H1. So these are the values are given the enthalpy. So with respect to the state 1, you can observe the value of the enthalpy, that is H1. Now we have the compression, that is isentropic compression. So you see these blue lines. These are the constant entropy lines actually. So now you have to follow the constant entropy line, okay, till the condenser pressure. Okay, so that pressure also you can measure by the device. So this is the pressure line of the condenser pressure, and this is the constant entropy line. So where these two lines will cut, that will give you the state 2. Then you can measure the enthalpy at 2 with the help of that chart. So now from 2, the condensation takes place, and that 2 to 3 process that is in the condenser. So you have to follow the same pressure line till that is reached to the saturated liquid, if it is theoretical one. Okay, so this is the 3. Then from this 3 you can find out the enthalpy S3, and then you have the expansion process or the throttling process. Now you drop the pressure till the evaporator pressure with same enthalpy line, because this is the isenthalpic expansion. So S3 that is equal to S4, and your pressure is reduced here. Okay, so like this, then like 4 to 1, that is the evaporation, already you know. So in this way we can easily observe the enthalpy at 1, enthalpy at 2, enthalpy of 3 and 4, both are same. So by knowing the enthalpies, actually we can do the analysis of that particular thermodynamic cycle. How much refrigeration effect we get, that is S1 minus S4. How much work we did in that compressor, that will be S2 minus H1. Okay, how much heat is rejected in the condenser, that is S2 minus S3. So that is the utility of the pH chart to do the analysis of the vapor compression refrigeration cycle. Now the performance index, again that is very important. So the performance index of the refrigerator, that is the COP, which is known as the coefficient of performance. Okay, and the COP of the refrigerator is given by the refrigeration effect divided by the net work input. So how much refrigeration effect you achieve by some particular input of the work, that is the COP of the refrigerator. Okay, and COP actually indicates its energy efficiency of the refrigerator, and it indicated by the star rating. As you see, when you go to the market to purchase the refrigerator or air conditioner, so there is a star rating. So that is actually as per its energy efficient ratio, you can say. Okay, so that is actually the COP. So COP will decide its running cost. So definitely the initial cost or the purchasing cost is high, because that is about the quality, but the running cost will be low because the COP is more. You can understand like that. If you have the two different phases of the different star rating, and you are getting the same refrigeration effect by both the refrigerator. Okay, if the star rating is high, for getting the same refrigeration effect, the net work input will be low. Net work input low means the compressor work is low. Compressor work low means the electricity consumption is low. So definitely you will pay less bill of the electricity. So the more stars a refrigerator has, the more efficient it is in conserving electricity, which translates to lower energy bills. So that is about the running cost. And definitely the star rating is a part of Bureau of Energy Efficiency, and that is the certification which is given by. Okay, so this is all about the domestic refrigerator, its component, its thermodynamic cycle, which is the vapor compression cycle, and we talk about how that work in that particular cycle. Okay, hope you understand how domestic refrigerator works, and definitely its thermodynamic cycle, vapor compression refrigerant cycle. Thank you.